Good morning. The title of the lecture is Dimension Modeling. This is the second lecture in this module. In the earlier lecture, I introduced the concept of star schema. In this lecture, we continue our discussion by discussing the other schema models, namely Snowflake schema and fact constellation schema. We also discuss the concept of aggregated fact table, different types of dimensions, and different types of fact tables. Finally, we conclude this lecture by introducing the concept of data mart and different types of data marts. Another alternative to level indicator is that normalize the dimension tables by attribute level, with each smaller dimension table pointing to an appropriate aggregated fact table, which results in the third kind of schema model called Snowflake schema. Why should we do this? As I mentioned earlier, when the cardinality of the dimension table is very large, then the inner select statement in the dimension table may take a huge amount of time in processing the request, so which leads to a source of delay. So in order to reduce the delay, what we can do is we can divide the fact constellation table by normalizing. I repeat, we can divide the fact constellation table into a set of smaller dimension tables pointing to an appropriate aggregated fact table. So this kind of structure imitates the structure of a snowflake. That is why we call this as a snowflake schema. Notice here that the stored dimension table generates subsets of records. First, all records from the table where level is equal to district in the star are extracted, and only those attributes that refer to that level, that means district description, for example, and the keys of the parent hierarchy, that is region ID, are included in the table. Through the tables, I repeat, though the tables are subsets, it is absolutely critical that column names are the same throughout the schema. The diagram shown on the slide is a partial schema. It only shows the snowflake of one dimension. In fact, the product and time dimensions would be similarly decomposed by considering product, brand, manufacturer hierarchy. Color and size are extended attribute characteristics of the attribute product, not part of the attribute hierarchy. So if you observe, in the snowflake schema, no level exists in the dimension tables. Dimension tables are normalized by decomposing at the attribute level. Each dimension table has one key for each level of the dimensions hierarchy. The lowest level key joins the dimension table to both the fact table and the lower level attribute table. But how does it work? The best way is for the query to be built by understanding which summary levels exist and finding the proper snowflake attribute tables, constraining there for keys, then selecting from the fact table. So that means by writing nested queries in SQL with proper conditions, we can take out the desired computation for each fact from the fact table. We discussed three different kinds of schema models: star schema model, fact constellation schema model, and snowflake schema model. We now discuss what are the steps involved in preparing the dimension model. There are 4 steps. The first step is define the business process, then ascertain the grain. That means based on the processing requirements, business process requirements, we have to identify and understand the grain and its level, then identify the dimensions, and finally select the facts. For example, point of sale for withdrawing money, the grain is individual line item. Dimensions are region, customer, product, and date. So the facts are, amount is the fact associated because withdrawal is the process, and balance. We now discuss what are the different types of facts that we can store in the fact table. There are 4 different types of facts can be considered into account while designing the fact table. They are fully additive, semi-additive, non-additive, and factless facts. Measures which are aggregated for all dimensions in the schema is termed as fully additive measure or fully additive fact. A fully additive measure will aggregate to a correct value no matter what levels and dimensions are queried, because we are considering all the dimensions. Semi-additive. Semi-additive fact measures which can be aggregated for a few of the dimensions only. Instead of taking all dimensions, if we consider only measures pertaining to certain kinds of dimensions, then we call the fact as a semi-additive fact. Measures which cannot be aggregated correctly across any dimension for a given schema is known as non-additive fact. Measures which do not contain a meaningful value is known as a factless fact. Because joining dimensions for this fact has no explicit meaning in itself. Usually, the value of factless fact, if any, is always 1. What are the different dimension types? There are various dimension types. Depending on the requirements of the business process, we need to identify the type of each dimension. The different dimension types are primary dimension, secondary dimensions, conformed dimensions, slowly changing dimensions, degenerate dimensions, and junk dimensions. We now discuss each dimension type in detail. Primary dimension. If any dimension contributes to the fact grain, then it is called a primary dimension. So when you consider the set of primary dimensions, they uniquely defines the associated fact. For example, sales fact is typically completely defined by store, product, and time. So therefore, store, product, and time are the primary dimensions here. Secondary dimension. A secondary dimension is a dimension when it doesn't contribute to the fact grain, which we also termed as non-primary dimensions. Examples for this kind are payment type, customer, manufacturer are still important for analysis of sales fact. Their secondary dimensions are generally useful for rich analytic slicing and dicing. For example, top 10 customers or top 20 customers, top 5 products. In that situation, we consider the secondary dimensions. Third category is conformed dimension. When a dimension table is used in more than one star schema, then such a dimension is termed as conformed dimension. For example, here the customer dimension is used by 2 fact tables, deposit fact table and loans fact table. So therefore, customer dimension is called a conformed dimension. What is the gain? When we consider a particular dimension as a conformed dimension, the advantage of using such a dimension, such a sharing, is that it saves work and effort because one table is being used for several purposes. The fact tables can be joined from different star schemas if they have conformed dimensions. For example, customer could be captured at the store card. I repeat, customer could be captured at the store by using a card swiping machine, which is a part of sales fact. And the same information be a part of marketing promotion strategy, which we call as a campaign fact. and also it could be served by call center for warranty replacements, which we call as a warranty fact. So in these three different fact tables, namely sales fact, campaign fact, and warranty fact, the same customer information is used. Employee may be a sales representative claiming credit for sales, which we also call as a sales fact, or maybe a finance manager authorizing vendor payments, which we consider as a vendor payment fact, or a call center person taking customer calls, service call fact. So employee and customer in these examples are nothing but conformed dimensions. Then the next type of dimension is a slowly changing dimension. In slowly changing dimension, the attributes are relatively constant, but they do change over time. That means dimensional attributes in this category changes over time. So we need to capture these changing realities as a history. So therefore, it requires special design techniques to keep it single valued for each fact row while still retaining history. For example, so there are three different types of slowly changing dimensions. They are termed as type 1, type 2, type 3. In type 1, we overwrite the previous values. So this we call as a slowly changing dimension of type 1. In type 2, we create additional time-stamped dimension record. Whereas in the case of type 3, we automatically preserve the history by using the concept of partitioning. I repeat, in the case of type 2, we can create additional time-stamped dimension record, or we can automatically partition the history. Whereas in the case of type 3, we create additional attribute column to retain any one previous values, which we call as a version of history. Then the other category of slowly changing dimension is hybrid. In this case, we treat some changes as type 1 and other changes as type 2, or some changes as type 2 and other changes as type 3. That means mixture of different types. If you consider, then it is called slowly changing dimension of type hybrid. In all these situations, we need to create the key. In type 1, we overwrite the changed attributes. That's why it's called overwriting in nature. In type 2, we create another dimension record. How do we create? By adding new rows. Type 2 rows have two date attributes, row effective begin date and row effective end date. Both attributes are stored as date data types. The purpose of adding these two attributes in a separate row is to mark the current row end date and add a new row. So by appropriately specifying the conditions, we can identify which set of records are related to the previous data and which set of records are current data with the change in the dimension values. Whereas type 3 preserves a version of history. This is basically used to track changes by including attributes such as original address, current address, etc. in the case of customer records. So based on the application requirements, we need to identify first what type of dimension it is, and in case it is a slowly changing dimension, to which category or to which type that slowly changing dimension is to be captured. This need to be decided while modeling the dimensions. The slide shows different types of dimensions for a slowly changing dimensions. Product here is slowly changing dimension belong to type 2 category, since a new row is added by marking current row with the field row effective end date and row effective begin date. It indicates whenever product details are changed in product dimension table, we can retain the data pertaining to old product details, and also we can store new product details. Suppose for a particular product, supplier has changed from a particular date, say. To retain details of old supplier and also to keep the details of the new supplier details, we add these date fields. Whereas in the case of employee dimension table, you can see employee name was spelled wrongly, so it belongs to a type 1 change. To retain current and previous positions of the employees, we use type 3 slowly changing dimension by adding current position as well as previous position attributes. So that means to say, to retain the history, we use addition of columns within the same dimension. That is the reason why we call this as a slowly changing dimension of type 3. So in the case of employee dimension table, which is of hybrid in nature, since both type 1 and type 3 slowly changing dimensions are involved. The next type of dimension is degenerate dimension. Sometimes a dimension may exist without any attributes, but they are useful for analysis. In that situation, we consider that dimension as a degenerate dimension. That is to say, a degenerate dimension is a single field that is not an element of any dimension, but which can be included in the fact table. So that means to say, it is permitted to remain as a field in the fact table because it is the only piece of information for that dimension exists. For example, voucher number is an example for the degenerate dimension in the banking application. Then another type of dimension is called junk dimension. Junk dimension is formed by a set of fields that do not fit into any dimension, which is used to hold a group of discrete attributes. There are generally also some pieces of data that are left over the fact table and the dimension tables have been shaped. A junk dimension naturally lack of hierarchy. All its fields are attributes. These attributes do not necessarily have some connection with each other. So this is a convenient way of grouping of random flags and attributes to get them out of the fact table. And we can retain only useful fields. We remove fields that make no sense at all. We remove fields that are inconsistently filled. And we remove fields that are of operational interest only, are some of the examples of junk dimension. There are other types of dimensions: role-playing dimensions, rapidly changing monster dimensions, large dimensions, and rapidly changing small dimension. When dimension appears several times in the same fact table, typically date and time dimension play many roles. Order fulfillment is a typical retail fact table having order date as one of the dimension table. Package date, shipping date, delivery date, etc. So the date dimension table role is changing here. That's why they are termed as role-playing dimension tables. We create one fact table key for each role. Rapidly changing small dimensions. This is same as a slowly changing dimension, except frequency is higher. If we need to track changes to attributes, we use this type of dimension. Employee attributes such as appraisal rating, we need to track. For example, telecom product, we need to track the changes, the attributes related to the telecom product. Rate plans keep changing. So the frequency of changes are very high, then we call this as rapidly changing small dimensions. Large dimensions. Size increases with a decreasing level of granularity here. Public utility companies, government agencies, when they keep human records in supermarkets, are examples of this kind. So for example, stop or stop. We did not create a slowly changing dimension to address slow changes or history. We choose indexing strategies to reduce the query runtime here. Then rapidly changing monster dimensions. These dimensions are similar to large dimension, but typical of a large insurance customer dimension. Customers and claims are rapidly created and changed. So we need to track history for credit and legal reasons. In a remote manner, continuously the attributes are changed to another dimension table because employees may move from one place to another place. So demographic change takes place here whenever employees moves from one place to another place. So in order to reduce we can reduce the cardinalities of such attributes by banding them. In the sense income band, credit band, etc. Then create all possible combinations of these attributes. We now discuss how to design fact tables for different grain requirements. There are three different columns shown here. One is for transactions, and another is for periodic snapshot and accumulated snapshot. If it is a transaction-oriented fact table, then we consider one row per transaction. If it is a periodic snapshot, one row per period is taken into account. If it is accumulated snapshot, the fact table row is over a life of complex process. Then coming to the insertions, insertion is, in the case of transactions, insertion is based on point in time. So point in time insertion means whenever a regular transaction is committed in the normal database application, at that point itself the insertion takes place. That is called point in time insertion. In the snapshot, periodic snapshot, we do insertion at regular intervals. In the case of accumulated snapshot, the fact table data is updated when each milestone is reached. Then flexibility point of view, transaction-oriented fact table provides maximum flexibility for analysis of a given process. Data may be kept at atomic level. That's why flexibility is maximum, because we can do any kind of summarization at any level by taking this atomic data. In the case of periodic snapshot, we can track multiple processes side by side. It is very good for scorecard-based applications. In the case of accumulated snapshot, I repeat, the accumulated snapshot is ideal for tracking multi-part processes. That is, claims, mortgage applications, etc. So great challenge exists for the transaction-oriented fact table design to compare different business processes. In the case of periodic snapshot, we need to identify the fact category, either a non-additive or semi-additive facts. Whereas accumulating snapshot, in accumulating snapshot, load performance may limit the deployment because of large size of data. We now discuss what are the different steps for designing a dimension model. According to Rolf Kimball, there are 9 steps. According to Rolf Kimball, I repeat, according to Rolf Kimball, we can design a good dimensional model by following the steps shown on the slide. The first step is choose the subject matter, then decide what a fact table represents, then identify and confirming the dimensions, then finally choose the facts. After choosing the facts, we store pre-calculations in the fact table, then optimize the dimension table data, choose the duration of the database, and track the slowly changing dimensions, and finally decide the query properties and query models. By following these 9 steps, we can design a good dimensional model. We now discuss what are the different types of facts. The facts are classified either value-based facts or summary-based facts. Numeric facts, count or occurrence-based, or non-numeric facts or belong to the category of value-based facts. For example, employees assigned to a project is a count. How many employees you have assigned to a project? It's a count. Comments in fact table is a non-numeric fact. Whereas additive, semi-additive, non-additive facts belong to the category of summary-based classification. For example, sales, number of total minutes are examples of value-based facts. Additive facts these can be added across all dimensions. Price, quantity sold are examples of value-based but semi-additive facts, because these can be added only across some dimensions. They cannot be added across the product dimension, as the fact total price does not make sense. Rather, average price across products makes more sense. Different types of fact tables are transaction-oriented fact table, snapshot-oriented fact table, or summary-oriented fact table. The transaction-grained fact table represents an atomic action that occurs at an instantaneous point in time. There is often no guarantee that a record for a given policy or a customer exists in the transaction fact table. A record exists only if a transaction occurs. Conversely, there is no upper limit to the number of records for a given policy or a customer. The date, timestamp, I repeat, the date or timestamp on the transaction record may be accurate to the individual day, or it may be accurate to the hour and minute. Normally, there is only one single fact, generically called amount. Meaning depends on the value of the transaction key. After posing it, we do not usually revisit the transaction grained fact record for any type of update. So in this figure, the policy transaction fact table is a star schema designed by taking 7 dimensions and 1 measure, namely amount. So the context of a transaction is modeled as a set of independent dimensions: policy, agent, covered item dimension, transaction time dimension, customer dimension, coverage dimension, transaction dimension. The measure transaction amount is in a fact table that refers to all the dimensions by foreign keys pointing outward to their respective dimension tables. So the clean removal of all the context detail from the transaction record is an important normalization step, and is why and that is the reason why fact tables are normalized. Kimball mentions 3 fundamental types of fact table grain. A transaction is a set of data fields that record a basic business event. Point of sale in a supermarket, attendance in a classroom, an insurance claim are examples of transactions. The measurements group nicely together into a single fact table with the same grain. So transaction grain is related to this portion, snapshot grain, and then accumulating snapshot grain. In the case of periodic snapshot, a snapshot is a measurement of status at a specific point in time. For example, in the figure, earned premium is the fraction of the total policy premium that the insurance company can book as revenue during the particular reporting period. So the periodic snapshot grained fact table represents predefined time span. That means by taking a particular time period into account, we are computing the grain here in the periodic snapshot. In the case of accumulating snapshot grain, it represents an indeterminate time span covering the entire history, starting when the collision coverage was created for the car and ending with the present moment. We frequently revisit the accumulating snapshot fact record to update the facts. Generally, there is only one fact record for the collision coverage on a particular customer's car. That record gets updated. So, by using the date field, claim payment to date, earned premium to date, and effective date, etc., we can capture the history. As history unfolds, we must revisit the same record several times to revise the accumulating status. This is a typical data model used widely in any organization or an enterprise. Here, the number of fact tables connected to several fact and dimensional tables. One can assess whether 3NF are good enough to represent. Of course, there are several approaches, but star schema is the most preferable approach. So if you observe how the interaction made across different dimensions and facts within an organization, pictorially shown here. This is a fact table, this is another fact table, these are several fact tables linked here. In a more elaborate way, we'll discuss how to model the dimension table. I repeat, how to design a dimensional model. First step, identify the subjects, that means dimensions. Identify the hierarchies of a dimension. Identify attributes of levels in hierarchies, and define grain. Once these are identified, then we need to use key performance indicators to identify the facts and group the facts in a logical set form. For example, transaction amount, number of bonds, number of transactions, service cost, etc. They're all related to financial transactions. Number of checks cleared, number of visits made to a particular branch, number of demat transactions, etc. belong to non-financial transactions. So KPIs basically helps to identify the facts and also to group the facts into a logical set. Here there are two different logical sets exist based on the facts, KPIs. One set of facts are called financial transactions and another set of group of facts are called non-financial transactions. Then step 3, then link the group of facts to the dimensions that participate in the facts. For example, what are all the related subjects that are required to measure these KPIs as facts in the financial transactions are linked here. For example, product, organization, channel, time, and customer. They are all linked here. Then step 4, define the granularity for each group of facts. Do you want to measure the facts related to financial transaction with respect to customer, scheme, branch, channel, day of hour combination, or weekly KPIs that need to be calculated weekly, quarterly, etc. But whatever it may be, the granularity must be identified for each group of facts. So the granularity identified for this group of facts of financial transactions is shown in the dimension table. Next topic is, what is the use of data marts? Data marts are databases that share many of the features of data warehouses, but the scope is very, very small. A data mart is defined as a subset of a data warehouse for a single department or function. A data mart may have tens of gigabytes of data rather than hundreds of gigabytes for the entire enterprise. As I mentioned, the focus is on specific subject areas. So it looks like a warehouse, but scope is limited to a specific subject area only. A company can have a data warehouse containing sales, inventory, distribution, finance, and human resources subject areas, and it may also have a sales data mart, an account receivable data mart, and an employee turnover analysis data mart, etc. Why do we need data marts? Users query only from data marts and never query from the warehouse itself. The two reasons for the need for data mart are shown on the slide. The first one is end users will get much better performance querying from a data mart than from a data warehouse. The reason is the size-wise data mart is very small compared to a data warehouse. So more quickly the user can get the answer. And at the same time, the data marts are related to either a subject-specific or department-specific activity. So end users will have a much easier time navigating through data marts. That is another advantage of using the data marts. And also the data marts help the power users to slice and dice the data as they like. Specific to their function, their need, they can manipulate the data mart. So the slide shows comparison of data warehouses with the data marts. Scope is restricted to a particular department, whereas for data warehouse, the scope is the entire organization. Several subjects are taken into account in the data warehouse, but single subject and a very large object is considered in the case of data mart. There can be many data sources in data warehouse, very less number of sources for data mart. Size is more than 1 terabytes typically used in data warehousing design, whereas for data mart the size is less than 1 terabyte. Implementation time may take several months to years to build a data warehouse, whereas it takes a few months to build a data mart. When data marts are derived from a data warehouse, then the data marts are called dependent data marts. The slide shows marketing data mart, sales data mart, finance data mart. All these three data marts are derived from a data warehouse of the enterprise. Independent data mart. When data marts are derived from sources, then it is called an independent data mart. That means it is not dependent on any of the data warehouse. So whenever we need a sales data mart, then you have to capture all the data from the sources and then perform the cleaning, then build the data mart. So here the slide shows a data mart pertaining to sales and marketing data mart, combination of sales and marketing data mart. Can a data mart replace a data warehouse? The data mart cannot replace the data warehouse. As time progresses, data mart with no data warehouse is likely to fail. The reasons for sourcing from a normalized warehouse are to avoid repetition of extraction, meaning that suppose if more than one data mart needs data from common set of source systems, in such a situation, every data mart accesses the sources independently, and each data mart should associate with a cleaning process and integrate the required data, which results in duplication of the effort. So in the presence of warehouse, effort duplication doesn't arise, since only once we are cleaning and integration are performed. That is why data warehouse avoids extraction of repetition. Then second reason, it ensures standard interpretation of enterprise data. By sending data through a common integration layer, ensures that all downstream systems have a common understanding about the meaning of each data item and the usage of each data item. When the data item is populated, for multiple sources, this is especially important. For example, when sales data flows in from multiple source systems, standardization is very much essential. Another reason is it provides repository that is far more flexible than denormalized structures in the high performance query or data mart layer. Data structures used in data mart are easy for users to understand but difficult for developers to build a large integrated enterprise-wide repository of information. That is why the normalized data warehouse is appropriate and data marts are likely to fail over a period of time. That is the reason why most of the enterprises uses the concept of dependent data marts by creating an enterprise data warehouse. Why a separate data warehouse is required? A separate data warehouse is required to improve the performance for both online transaction system as well as warehouse system. DBMS, you all know that DBMS is tuned for OLTP. So it has a full-fledged support exists by, I repeat, it has a support for better access methods, indexing, concurrency control, and recovery procedures. Whereas in the case of warehouse, I repeat, the warehouse is tuned for OLAP processing. Complex OLAP queries, multidimensional view and consolidation are the key objectives of building the data warehouse. Of course, missing data needs to be very carefully handled, and data consolidation is also important. Quality of data is also important. Operational databases do not typically maintain the historical data. That's why even if some data is missing, we don't care. But in the case of decision support system, we need historical data for analysis. Therefore, we need to minimize the missing data. Consolidation is also important for a data warehouse. Decision support requires consolidation of data from heterogeneous sources. Different sources typically use inconsistent data representations, codes, and formats which have to be reconciled in order to maintain the data quality. So the recommended approach for building a data warehouse is shown on the slide. First of all, we have to define a high-level corporate data model. Then take a small business activity or business function pertaining to a subject-specific or department-specific activity. Then build a data mart, refine the data marts. Then as and when the number of data marts are more and unmanageable, then apply the concept of integration of data marts to build an enterprise data warehouse by grouping all these data marts functions together into a single integrated company-wide enterprise warehouse. If you are not able to manage the enterprise data warehouse, then you can go to different layered approach, multi-tier data warehouse. So even you can also use distributed data marts. The functionality of the data associated with each data mart is distributed across the different geographically distributed, and then if you are not able to manage even the distributed data marts, it is better to have a multi-tier data warehouse. But in a way, to start with, first of all, we should have a high-level corporate data model, which is a document, written document, which needs to be prepared by understanding the requirements of the enterprise. Conclusions. In this lecture, we discussed Snowflake schema and fact constellation schema. We also discussed different types of dimensions and different types of fact tables. The lecture is concluded by defining the concept of data mart and how data marts are useful in building the corporate data warehouses. Thank you.